This should be the last screencast for Chapter 15. We have 3 topics, 2 of which are very interesting and important pieces of physics equipment. And one is called Gauss's Law, which is a little bit more technical. We begin with the Millikan Oil Drop experiment, obviously named after somebody named Millikan. And here we're talking about this period of history right here. And he died the year after I was born. He was a very, very strong, faithful, practicing Christian. He was known for his humility, but he was also known for his willingness to speak out, for example, in the field of ethics. If you think about it, we need ethics to form a foundation for science. Science cannot come up with ethics. However, we don't need science in order to form ethics. Ethics needs to inform science. Science cannot form ethics. It shows a natural limitation of science. Science cannot be the only way of knowing. This Robert Andrews Millikan was a pretty brilliant guy. He had received 25 honorary doctorates. So I guess you had to call him Dr., et cetera, Millikan. He founded Caltech, which is one of the competitors on the West Coast with the MIT, Massachusetts Institute of Technology on the East Coast. He was very critical of Darwinian evolutionary theory as being incapable of truly explaining diversity, truly explaining beauty and complexity in all of the different designs. He often looked at aspects of God's creation and used the phrase, the great architect. And you've heard me say on numerous occasions that when we see design and complexity, we expect there to be an architect because it's the only explanation. He received a Nobel Prize for this particular experiment in 1923. So it involves an oil drop. And in order to talk about that, we're going to come all the way down and focus on this picture right here. So what we have are 2 metal plates. Here's one metal plate up here, probably copper. Here's another metal plate down there, separated by some distance d. Now, this whole contraption, at least this part here in the box, could be a little bit larger than the palm of my hand. So we're not talking about something that's necessarily very large. And we're going to take these 2 metal plates and we're going to hook them up to a power supply. And the picture doesn't show it, but it would be a variable power supply, meaning we could vary the voltage. The top plate is going to be hooked up to the positive, and the negative plate is going to be hooked up to the negative post. And we can vary that voltage. Maybe there'd be a rheostat in here or something. And so that we create a variable electric field inside these 2 metal discs. And the electrical field, of course, is going to go from the positive to the negative. And the other thing you don't see in the picture is surrounding these 2 discs would be a barrier. It just could be a simple piece of cardboard going all the way around. That would eliminate any air currents that might get between the 2 metal plates. Now, there would be a window in the metal plate over here, in the cardboard or the barrier, whatever it is over there, so that your telescope, you're going to be looking over here, you can look through the window to see what's going on in between the 2 metal plates. Now, it would be dark in there, of course, if there wasn't another window on the other side with a light source. And that light shines and illuminates the inside of this short cylinder. And you'll notice that there is a little hole in the very top of the metal plate, in the positive plate. The next thing that Millikan did was he took an atomizer, the kind of thing that they used to dispense perfume and cologne with, and when you squeeze this little rubber ball here, Bernoulli's principle, the air that shoots out here picks up some of the chemical that's inside the container. Well, if inside the container you have some oil, you get this mist of oil drops coming out. And the oil drops don't have the same size, and they're also not going to have the same static charge as they go through the air and pick up some electrons. Now, if you're very, very careful, there's a good chance that one of these drops is going to drop through that hole and end up inside the container, inside this cylinder with the top and bottom metal plates. And so now you can see it right there. I just colored it blue. Now gravity is going to bring it down, and if it's falling, you're going to have a little drag force acting back up. But because of the fact that it's negatively charged from the electrons, you can attract it to the positively charged metal plate on top. Remember, it's connected to the positive post of the battery. And by varying the voltage, you could make this electron go up and down and up and down. Or you could make it just sort of hover. And when it hovers, then you're at equilibrium with the net downward force equal and opposite of the net upward force, which would equal the charge on that oil drop times the magnitude of the electric field. And you can solve this equation when you're at equilibrium for Q, the charge on the oil drop. Now keep in mind the reason for that charge on the oil drop is because of one or more electrons. And when you're looking through there, the oil drops don't travel very rapidly, hundredth of a centimeter per second, so you can literally follow them as they move. Now, Millikan did this experiment 1,000 times, many, many, many times. And every value he got for Q likely could very easily have been different because every oil drop would have a different value of Q because the oil drop would have a different size. And even if they didn't have different sizes and were somehow coincidentally, big coincidence, all exactly the same size, they would have different amounts of static electricity that they would have picked up. And from this information, Millikan was able to deduce to 1% precision what is the charge on an electron. Look how small the charge is, 10 to the minus 19th coulombs. It's arguably one of the smallest known particle in the universe. So to find that charge is pretty remarkable, and hence the Nobel Prize 101 years ago. Now, what he did was he took those 1,000 data points, 1,000 Q values of Q, and he said, what's the biggest number that can go into all of them? And the biggest number that could go into all of them, and incidentally, they went in by multiples of that big number, 1 times, 2 times, 3 times, 4 times that particular number. That, by deduction, had to be the charge of a single electron. Obviously, you can't have part of an electron and get part of that value of Q. Now, an analogy might be like this. Imagine you had a scale, like a sensitive bathroom scale, and you wanted to measure the mass of a single sheet of paper. And I'm using mass now instead of charge to illustrate the point. Well, let's imagine the scale cannot mass a single sheet of paper. It's not sensitive enough. But let's suppose that you took a handful of paper, 500, 250, 300, 427 sheets of paper, and put it on the scale and massed it. And you did that about 1,000 times with many, many different clumps of typing paper, of computer paper. Eventually, you would have enough data that if you were to find the biggest number that went into every single one of those masses, by all logic, that should be the mass of a single sheet of paper, because you would have a multiple number of sheets of paper in every one of those stacks that you grabbed to put on the scale. So that's the Millikan oil drop experiment, which 100 years ago came up with the charge of an electron, which is very, very remarkable. Now, the Van de Graaff generator is another interesting toy. I remember in elementary school, And my younger brother and I would often get presents at Christmas from my dad and my mom. My mom would not give me science-like presents, but probably practical presents, maybe books or clothing. Usually my grandmothers took care of the clothing. But my dad would always come up with some type of science-like experiment. And my brother is a retired chemist. And one of the toys that we got was called a atom smasher. Now, it didn't really smash atoms. It was actually a very small Millikan Oil Drop experiment, maybe 7 or 8 inches tall. And it had a little bulb at the top, like you can see here pictured in red. And it had a belt that would bring a charge up to the metal ball. And then you developed a static charge, and you could do experiments in static electricity. And we had a lot of fun with that. We had all kinds of science toys, many of which that were not entirely safe by today's standards, and you wouldn't even be able to buy them in order to give them to a child. In any case, the Van de Graaff generator was a way of storing or accumulating a huge static charge that could create these miniature lightning bolts, if you will, and those lightning bolts could ionize air, and you could do other things with those lightning bolts and investigate electrical fields, which is what this portion of the chapter is about, as well as the effects of static discharges. So the device works something like this. And the one we have in school is about 1 meter high. The one at the Van de Graaff, the one at the Magic House, the Van de Graaff generator at the Magic House would be several meters tall, quite big. And the bigger the globe up here, in terms of radius, maybe we made it bigger, the greater the amount of static charge we could accumulate, and the longer our lightning bolts would be, and when they eventually would discharge through the air. Incidentally, it takes approximately 30,000 volts of potential difference per charge to go through about a centimeter of air. So that would be about 75,000 volts to go through an inch. And in our Van de Graaff generator, it would not be uncommon for a person who's playing with it to get 100,000 volts of electricity every time they got shocked. Now, that shock could be irritating, but it would not be dangerous because it's the amount of current that's dangerous, not the amount of voltage. But that's a good number to remember, 30,000 kilovolts per centimeter, in order for an electrical charge to have enough energy to go through a centimeter of air. Obviously, it would be slightly different in different types of atmospheres or in a vacuum. Now, what we have here is a motor that's making the belt go in this direction. And it's going to come up and around, and then it's going to come down here. And when it comes down here, it goes by this wire right here that's going to drop off all the excess electrons into the ground. In other words, all these negative electrons, they're the mobile charged particles, will be dumped into the ground. So this whole device technically is grounded. And then the belt comes up here to pick up more electrons, leaving behind a net positive charge. And this globe is going to become more and more and more positive until the potential difference reaches about 30,000 kilovolts, at which point it could begin to discharge through the air, ionizing the air, if it did not have some other better pathway or conductor to travel through. This is the Van de Graaff generator. Sometimes you can smell a little bit of ozone produced when a discharge of electricity goes through the air. That high voltage can break that ozone, can break oxygen molecules apart and turn it into ozone. So that's the Van de Graaff generator. Ways of creating very, 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 very high voltages in order to do your experiments. Now, the last part of the chapter is a little bit more technical. It's a little bit more difficult, but fortunately, it's not covered in that much detail on the AP. In fact, I don't think it was too many years ago that they didn't have Gauss's law on the AP exam at all. And nowadays, I've noticed that there are some mentions or references to Gauss's law. Gauss's law, named after Carl Friedrich Gauss, and just like Van de Graaff, both men were German, probably had some Lutheran heritage, as many, many people during this period of history had a Lutheran background. That doesn't necessarily mean they were Christians. Many times scientists did not write very much about their faith. And so we don't necessarily know unless we have evidence from the writings of other people about them, about what they may have believed. It is tragic, though, during World War II in particular, to read how Hitler sort of co-opted the broader German Lutheran Church in order to cover for him in some of the horrible things that he was doing. In any case, the Gauss's law is a way of studying electric fields, and it's used to calculate the average electric field, and the average electric field is represented by the letter E, and remember, it's the ratio of the force per charge, and its units, of course, would therefore be newtons per coulomb. The strength of an average electric field on a closed surface. Now, by a closed surface, we mean a surface that has both an outside and an inside. So if you're looking at this picture right here to the left, this is a piece of surface, let's say from a shoebox, made out of cardboard or wood or or paper, some other material, so that there was an inside and was an outside. It's not just this piece of paper without anything that around it. It can also be used for spheres. It can also be used for cylinders, where you have a top and bottom that's closed off. So any closed surface, we would be interested in knowing what is the electric field around the outside of that closed surface. What is the electrical field either on or inside the material of the closed surface? And what is the electrical field in the emptiness inside the closed surface? So in the picture here, you see the electrical field lines, and electric field lines are often, we use vectors to represent them, going from positive to negative, and we also often refer to them as flux. The higher the flux, the stronger the electrical field, and so we're going to draw it with more and more arrows. If we have a very weak electrical field, then we're not going to draw as many arrows to represent the strength of that electrical field. So you can think of flux as a measure of the amount of arrows, where each arrow represents a certain amount of strength in the electrical field. And Gauss's law states that the electric flux, reading down here, through a closed surface is proportional to the charge contained inside the surface. The more flux lines you're going to draw going through the closed surface, that implies that you have a strong charge inside the surface. Now, the unit for electric flux is called the phi. And I think it might be helpful to remember, in order to pronounce this correctly, is that flux begins with the letter F, and phi, in terms of how you pronounce PHI, begins with the letter F. So this is the electric flux, and from earlier in the chapter, the electric flux equals your electric field strength times the cross-sectional area. The cross-sectional area would be this surface right here in the background, or whatever your surface happens to be, and it would be, of course, meters squared. So, moving along, keep in mind that when we measure our angle, you might recall from way back in first quarter that we said that work was defined as force times distance, as long as the force was acting in the same direction as the distance. But if they weren't, and there was an angle between the two, then you were interested in the parallel component, which gave you the cosine theta. Well, we have that same thing right here. Those flux lines equal the electrical field strength times the cross-sectional area. Or we could also begin like this. My electrical field strength is going to be my charge per the cross-sectional area, which would be meters squared, that the flux lines are going through. And if they're not moving in the same direction, then we need to throw in the cosine theta. Remember, the word normal means perpendicular to that surface. Another point down here, by convention, by agreement by physicists over time around the world, for a closed surface, the flux lines passing into the interior of the volume are negative, and those passing out of the interior of the volume are positive. I hope I said that correctly earlier on. So we would call these negative and these were positive. Now, if we look at some problems here, and this can be a little bit tricky, consider a uniform electric field oriented in the x direction. So here's my x-axis right there. And so imagine I have all these electric flux lines going in the same direction as the x-axis. Now, find the electric flux through each surface of a cube. And of course, there are 6 surfaces in the cube: top and bottom, left and right, front and back. So to begin, let's change color here. Let's look at the xy plane. The xy plane would be this one in the back and this one in the front. There's my 2 planes in the xy plane. And you notice that these planes are running parallel with my blue flux lines. So therefore, cosine of 90 degrees equaling 0, I have 0 flux due to this surface in the very back, and I have 0 flux due to this surface in the very front, because there's no flux lines that are perpendicular. So now I'm going to erase those 2. And now let's come down to the xz plane. And in the xz plane, remember here's the x-axis here, and here's z. We're going to have this surface at the bottom and this surface at the top. And again, my flux lines are not perpendicular to either surface. And therefore, the top surface is going to contribute 0 flux, and the bottom line is 0. And now we're ready to move on to the remaining 2 surfaces. So in the remaining 2 surfaces, and now we're down to the YZ. In the YZ, we've got this surface right here on the left, and this surface towards the back on the left, and this one here is on the front. And now you can see your flux lines are normal to these surfaces. They're normal in the back as they come in, and they're normal on the right as they come out. And so when we take a cosine of 0, we get 1, and the cross-sectional area is length times length, or length squared, and these on the left side are negative, these on the front side are positive, so we have negative EL squared and positive EL squared, and when we add those up, they cancel each other out, and so we have 0 plus 0 plus 0 plus 0 plus 0 plus 0 equals 0 flux. And we would not expect there to be an electrical charge inside. All right, let's take a look at Gauss's law a little bit when we have a curved surface, like on the surface of a sphere. Now you might remember Coulomb's law goes all the way back to this, where we have Q1, Q2 divided by the radius distance between them squared. And if we multiply both sides by r, not r, that's for a different derivation. If we divide both sides by Q2, it disappears I'll redraw it again. There's Q2. If we put a Q2 down there, we have to put Q2 down there. These Q's cancel out. And remember, force per unit charge is also known as E, electric field strength. So therefore, we get that equation right there. But now when we talk about our area, remember E also, when we multiply both sides by my area, here's area there, here is area there, and area on the surface of a sphere is 4 pi r squared. And so phi equals E times area times this, and that's going to give me this value right here, 4 pi k with a subscript E times Q. Now this 4 pi constant to the subscript of E is the reciprocal of that is sometimes called epsilon sub aught, O-U-G-H-T, aught meaning 0. Okay, epsilon sub aught. And it pops up in a lot of different places in physics. You're also going to see it again later on in fourth quarter. And it has a very, very precise value. Here it is to 3 places. We know it up to 12 places. And interestingly enough, if you vary that last place, even just a little bit wiggle up or down, then none of what we're talking about right now is going to work. In fact, there are a lot of things that would cease to be possible, and you certainly would not have a universe like we know it today, because this number is fine-tuned. But here's what we have it to 3 significant digits. And so you can use epsilon sub aught, or you can use the Coulomb's constant to the little letter E power. It's strictly a matter of taste. And this value right here is going to be given to you. Obviously, 4 pi is a constant. This is going to be a constant, and we're going to be looking at, your value of Q can vary. Now, I will say that this epsilon sub aught is called vacuum permittivity, or the permittivity in free space. You might say, what do you mean by permittivity? What are we permitting? Well, in a sense, what we're permitting or what we're allowing is what we would call a limit. There is a limit to the amount of electrical field that can be in a vacuum. So the vacuum permittivity is the limit of the electrical field strength in this in a vacuum. The electric field density, excuse me. And this is going to be true for any closed surface. And usually we, in a lot of times, because surfaces aren't always symmetrical, we can use it to obtain the average electrical field. And I don't like those lines because they were not straight. So it's for any closed surface. And we can use calculus to derive it for others, and it can always be used to obtain the average electric field on any surface. And so this is the equation that you would be given on a test. Now over here you'll notice they talk about a Gaussian surface as an imaginary surface. And you'll see that a little bit in this next discussion. Now, if you want to stop at this moment and take a few minutes to kind of look over this problem and understand it before I talk about it, that would be a good idea to pause your screencast for the moment. But in any case, this can be very confusing because you'll notice that the letters A and B and C and D here do not correspond to the A and the B and the C over here. In fact, this whole discussion on the right, figure 15.29, really just goes with part A up here. And so we begin with a sphere, and this sphere, being a sphere, is symmetrical. and it does have a certain thickness between the outer and the interior surface. And the electrical field lines are going from positive to negative by convention. They're going from the inside towards the outside. You would know that the electrical field on the inside would equal 0 because all the electrical charges would migrate to as far away as they could get from each other, which would end up being on the outside of the surface. That was talked about in an earlier screencast. And so we would imagine, for example, 3 possible scenarios. What would be the electrical field inside this material? What would be the electrical field if R is less than A? R being some imaginary equidistant distance from the interior of the sphere. And that would be your imaginary Gaussian surface. Or what if R is greater than B? And so R being the distance all the way around in 3-dimensional space, not a flat surface like this, at some point that you choose, and there's my spherical imaginary surface that is bigger than B. So that explains those pictures. And coming back over to this part of the problem over right here, we begin with a positive Q, hence you've got these positive symbols throughout here. And then later on they say, okay, what if we put a -2 charge in the middle? And that, of course, is going to change everything around. And that's where the solution set comes in. The solution to this problem, here my electrical field strength times my area. My area is 4 pi r squared because it's the curved surface, part of a curved surface of the sphere. And, of course, inside, where r is less than a, it should equal 0. Where r is bigger than b, outside the object, we're going to just get this value here, which of course is totally dependent on what is r and what is q, r being the distance to the imaginary Gaussian surface and q being the magnitude of the charge. Now, the last thing I want to do is look at this problem right here. We have a non-conducting plane. So this piece of this surface here could be wood, paper, tar paper, plastic, plexiglass, rubber, some non-conducting material. Obviously, if it was metal, you would not have a charge in the middle of it because the charge would only be on the surface. And notice here that if we choose a Gaussian surface, that's sort of a cutout circle in the middle there, and we extend it up some distance to have our imaginary Gaussian surface. I'm not quite sure why they chose to pick a particular sphere a cylinder like this. But remember our electrical field lines, as they go away from my surface, positive to negative, these would both be positive. If somehow I managed to charge the material so that it was negative, and again, you can't do that if it was metal, because those delocalized electrons would all go to the surface. Now your electric field lines would be going towards the interior, pointing towards the interior. Now remember that flux up here equals your electric field strength times your cross-sectional area. So if we look at this equation right here, where phi equals q divided by epsilon sub aught, that's the constant that's radius dependent. And then you look at this equation right here, that the charge on the inside of this material is equal to something I don't think you've seen before, sigma times A sub aught. And this is my charge per meter squared. You might be familiar with capital sigma, which means summation of This is lowercase sigma. And you can see that if I'm multiplying sigma, which is this, times cross-sectional area, which is meters squared, my dimensional analysis gives me Q. So if I take this equation right here, and what I'm going to do is I'm going to divide this equation up here, divide left and right side by area. So since Q is going to equal sigma A sub O, so here's my Q right there. There's my Q, sigma A sub O. And I'm going to divide by my area. And you notice this problem says the electric flux is coming in one side perpendicular and going through the outside. So I actually have two surfaces. I've got to double my cross-sectional area. I divide by that because I'm dividing both sides by A, dividing this side by A, dividing this side by A, and that's what gives me this. My A's cancel, and I end up with this value right there. And I think that concludes our discussion of this chapter.